Okay, this is Jack Jackson back, and we're in our series of problems where we're trying to work out some first derivative, second derivative, and the tangent line at x equals 1, given the formula for a function. This time we're going to look at the function f of x equals 3 to the power x squared times e to the power 4x. So see if you can work this one out, and start by finding the formula for the first derivative. If you haven't done this already, work it out now. Press pause. Okay, well, you're back. Hopefully you've tried this yourself, and notice that there's going to be actually two ways I'm going to work this one. The first way is to work it just like basically like it is, and realize that we're going to eventually need to do a substitution. So I'll let u be the x squared and w be the 4x. So it's the derivative of 3 to the u times e to the w. And the last thing you do when you work this problem out is the multiplication. So it's the product of these two factors. So we use the product rule. Product rule says it's the first factor, 3 to the u, times the derivative of the second, that's the derivative of e to the w, plus the second factor, e to the w, times the derivative of the first. There we go, derivative of 3 to the u. Now, the derivative with respect to x of e to the w is e to the w times the derivative of the w. The derivative of 3 to the u, remember, is natural log of 3 times 3 to the u times the derivative of the u. This might be a little bit easier to see if I go ahead and write this there, which is where it sort of naturally occurs. Now, in the next part, this is 3 to the u, e to the w. The derivative of the w, let's see, w is 4x, so the derivative of 4x is just 4. U is x squared, so the derivative of x squared du is just 2x. Now, here I rewrote the natural log in the front and wrote this. We got e to the w and 3 to the u. So let's see what we've got here. If you notice, the 4 has a factor of a 2, so does this 2 here. So that both terms here have a 2 in them. They both have a 3 to the u and e to the w, so I pull that out front. Now what's left? Well, when I divide this, the 3 to the u, the e to the w cancels, and 4 divided by 2 is 2. Divide here, we get natural log of 3. That doesn't cancel. But the 3 to the u and the e to the w cancels, and the 2 cancels, leaving me just the x times the natural log of 3. So I get, finally, 2 times 3 to the u, but u is x squared. E to the w is 4x. And then I get 2 plus natural log of 3 times x. So that's method 1. Now another method to do is to use properties of exponents and rewrite everything with a base of e. So I use the property that e to the power natural log of 3 is another way to write 3, then use a property of exponents says I can multiply these together. And so this is natural log of 3 times x squared. And here, if I have the same base, I can add the exponents and get natural log of 3 times x squared plus 4x. So now this is just e to the, let's call it v power, where v is this whole thing here, like this. Well, that's a pretty easy derivative to do. Derivative of e to the v is e to the v times the derivative of v. So then we're taking the derivative of this, which is just a quadratic equation, so quadratic function. So 2 times natural log of 3, and the power goes down to 1. The derivative of 4x is just 4. And so that's our answer. And so we could write it as e to the v, which is again this thing right here, and write it this way. Now this part, this e to this power, is exactly the 3 to the x squared times 4 e to the 4x. So those are both the same answer. And it doesn't matter which order I write these two pieces right here. So either way we write it, we can write this way or this way. We get the same thing, different form for the answer, but the same derivative actually. So how can we check this? Well, using a graphing calculator, we can go back to the original function, 3 to the x squared power times e to the 4x, and put that in as y1, as you can see here. Let y2 be the numerical derivative of y1 with respect to x evaluated at x. Let y3 be our answer. I use this version right here, I think. Yeah, 2 times 3 to the x squared times e to the power of 4x. Be sure you put parentheses around those powers. And make sure this is not in the power. This is down here, times 2 plus natural log of 3 times x. And the tables for y2 and y3 should match, and in fact they do, so that checks our work. Okay? Alright, now take this, either version here, and find the second derivative if you haven't done that already. Okay, so if you haven't done it already, do it now. Press pause. Okay, well, let's see here. I think I used the second version. Okay, this is our original function, which we could rewrite here. And here's the second version here of the derivative. Okay, now let's check. Let's do that. Well, first thing I did is I pulled the 2 all the way out front, and then used the same substitution. V is natural log of 3 times x squared plus 4x, same as before, same as this second version, V right here. And then what do I do here? Now I have e to the v times this linear function, natural log of 3 times x plus 2. And so I use the product rule, because this last thing we're doing here is multiplying these together. So use the constant multiple rule first, then a substitution, and now I'm using the product rule. So it's the first times derivative of the second, plus the second times derivative of the first. This is just linear, so the coefficient is the derivative, which is natural log of 3. And e to the v, the derivative is e to the v times the derivative of v. Now the v is this quadratic, so its derivative, like we did before, is 2 natural log of 3 times x plus 4x. The rest of this was recopied. Now here's our addition right here, so there's 2 terms. This is one term right here, e to the v times natural log of 3, plus, and the rest of this is all another term. So they both have in common an e to the v, so I factor that out, and that leaves a natural log of 3 for the first term. For the second term it leaves, let's see, that's gone, so it leaves, well actually these are the same thing. If I factor a 2 out of this, then I get natural log of 3x plus 2, which is the same as that. So it's 2 times natural log of 3x plus 2 squared. I can leave it, I'm going to leave it like that, although in fact it's really just a quadratic polynomial. If you wanted to, you could square this out, distribute the 2, and then put that with the constant term and see it would be a quadratic polynomial expanded out. But I'm going to leave it like it is there and just substitute back in what v is. If we want it written more like the original function, remember we can, this e to the v power is just our original function. So I can rewrite it there, that part right there. And I checked that one with the functions, with the calculator. Since I already had y3 typed in the derivative, I just went back to y2 and said take the derivative of y3. And then put y4 as the second derivative, and y2 and y4 should match. So I turned off the table for y3, kept the table for y2 and y4, and sure enough they did match. Notice how I put in the formula there. Here, watch your parentheses. I put it in like I did here, basically. So that checks, so that's good. Now to find the formula for the tangent line. Well, we have to evaluate the original function was x is 1. So put in a 1 here, and here we just get 3 times e to the 4th. You see the details worked out here. Or you can put it in this version right here and put in a 1. Either way, you get 3 times e to the 4th, or e to the natural log of 3 plus 4. It's the same thing. And to take the derivative formula, I believe I took, which one did I take? I took the version here. Not that version. I took the original version here. Put in a 1 here and here. So again, this is a 3 e to the 4th. Then we have a 2. So that makes a 6 e to the 4th. And then times that with a 1. So let's see, we're doing that again. 1 squared is 1. 3 times 3 to the first power is 3. Times 2 is 6. 4 times 1 is 4. E to the 4th power there. And this is natural log of 3 plus 2, or 2 plus natural log of 3, either way you write it. And there we get it. So that, all of that together is the slope. So that's the coefficient here. 6 e to the 4th times parentheses 2 plus natural log of 3. Notice that's just a constant. E is a constant. All this other natural logarithm is just a function that produces a constant output for a particular input, a specific output for a specific input. And so this gives you a specific number. Granted, it's a irrational number, but there's a number for the coefficient that's our slope, which is our value of our derivative. Then we have x minus the x-coordinate of the tangent point, which is x is 1, plus then the y-coordinate of the tangent point, which is this right here. So 1 comma 3 e to the 4th should be the point right here where both the original graph, which is in blue, and the tangent line, which I believe is in purple, where those two cross each other. And let's see, looks like the derivative is in red and the second derivative is in green. And we see the graph here. Let's see if we can take a look at some more things that we might see here. Well, notice 3 to any power and e to any power are both positive. So the original function is always above the x-axis. And you see it's always above and never actually really touches the x-axis there. So the derivative is, the first function is always positive. So there is some minimum actually there somewhere on that, and it never actually gets down as far, it gets real close, looks like it, but it never actually touches the x-axis. Okay, that's something, by the way, you can't really tell from this, looking at this picture, but we can tell because we know something about the formula. So this interplay of using the graph and the formula together, and the table even for that matter, the graph, formula, and the table all together really helps us understand what's going on with the function, whereas it's a little hard to tell from maybe just one of those three. Also looking at the formula for the derivative here, we see that this first part, whether you write it this way or this way up here, this first part, this coefficient, all this, is always positive. But this could be 0, and when it's 0 is actually at -2 over natural log of 3. So -2 over natural log of 3 is, I don't know, somewhere in here, is going to be where the first derivative goes up and actually crosses through and goes to the other side. And at that point, wherever that is right in here, where the red one crosses the axis, the blue one will be at a minimum. It might be useful to zoom in on that part of the graph and you can see that. Let's see what else. The second derivative, again, this first part here is always positive, but this part could be 0, and so we would take. Actually, it can't be 0. Look at what's happening here. You're taking something here and squaring it. That's positive, or 0 times 2 is positive. It's at least 0 or bigger, and we add log of 3. This whole factor has to be at least log of 3 or bigger. So the second derivative is never actually 0. It's always above the x-axis. Now, since the second derivative is always positive, the original function is always concave up. That seems to be reasonable for what we see here. The first derivative then is negative over here, crosses at that whatever point I said a while ago, and then goes into positive. And so that means the original function is decreasing and then increasing. We see the tangent lines here where we expect it to be, and close by, the original graph and the tangent line look pretty much the same. So, once again, everything seems to be checking out. We've reinforced our ideas of what the relationships are among the original function, the derivative, and the second derivative graphs, what one tells us about the other, and also about something about the tangent line. We used our calculator to check. Reviewing back here, we did a substitution. We used the product rule, and we used the exponential rule with the chain rule, both here and here, both with a base of e and some other constant base, and worked that out. Did a little factoring using the distributive property, or common factor factoring. Here we use some properties of exponents and logarithms to rewrite it to begin with, and then we worked it a different way. Down here, again, we took the first derivative in this form. We used the constant multiple rule, then the product rule. Product rule then led us to a couple other derivatives. One was just a linear. One was an exponential with the substitution. So we did the substitution or chain rule there. Then once we got here, a little algebra is factoring. So typically what we like to do is we like to have our derivative and second derivative factor, because one of the most important things is to find out when those values are actually 0. So in our next video, we're just going to do a pretty basic rational function here and find its first and second derivatives and a tangent line when x equals 1 for it. Again, I encourage you, when you do that one, check it with your calculator like we did here. Graph all three of them in your calculator or on your computer and see if the characteristics of the graphs match out. Once you've kind of done this on your own, come back and we'll watch it in the next video.